Okay. So hello for those of you joining online, and also those that are watching the recording. We're going to be getting started now. So yes, this is our workshop from CPMsoc, and I don't know why it says LaTeX Number Theory Workshop, but CPMsoc and SecSoc Number Theory Workshop. The focus will be on number theory, motivating applications in cryptography. So CPMsoc we will be going through some of the competitive mathematics side of number theory and the more theoretical side, whereas SecSoc will go through more of the applications in cryptography. So I believe the YouTube stream is working well. I'll have to check that. But without further ado, I'll hand it over to our first presenter from CPMsoc, which will be Ver. So you want to take it away? So just put this in the pocket.
Sex. Oh wait, I'll probably temporarily turn it on.
Yeah. Sure, and you can use the mouse if you want to change the slides.
Oh, thanks. I just thought, wait, can I use the arrow keys?
Yeah, that's fine.
Thanks, yes. Ooh. Hope everyone's hyped about number theory. Wait, the screen's kind of frozen. Maybe can I just click this button? Freeze images. Thanks. Yep. Hope everyone's hyped about revision. This is just fundamentals. This is, well, the first most important result in number theory. What is A equivalent B in mod n? Any ideas? I mean, just oversimplify. When you say A equivalent B in mod n, that means A and B have the same remainder. So we can define A and B as, same remainder when divided by n. So we can define A and B as first scalar multiple of n plus the same remainder. And this is why when you take B minus A, that's actually a scalar multiple of n, which explains, as you guys can see on the slide, why n divides into A minus B or B minus A. That's a key result, yes. And here are some nice examples. As you guys can see, the first number, 67 is basically 6 times 9 plus 13. And negative 41 is 4 minus 9 times 5. As you guys can see, these are sort of the remainders. When you take it in modulus, it gets simplified down. Four plus.
13 sounds like a 9 in it, like frick out.
Oh yes, sorry, silly me. Yes, so that is a key result. I guess this is revision. So here are some important properties of modular arithmetic. This first one is really important. N in mod n is equivalent to 0 because n divides into n. There's literally no remainder. The next one is if A is equivalent to B in mod n, then A plus K is equivalent to B plus K in mod n. And if you guys really want the algebra proof here, it's literally this. If A is equivalent to B in mod n, then A minus B is equivalent to 0 in mod n. That also means A plus 0 minus B is equivalent to 0 in mod n. Now, this is a pretty common high school trick, but A plus K minus B is equivalent to 0 in mod n for an arbitrary K, and then A plus K minus B plus K is equivalent to 0 in mod n, and then when you move that part aside, you have the result A plus K is equivalent to B plus K in mod n. And that seems pretty chill, right? We'll get to more tastier stuff too later in the revision. And next you have this result, is if A is equivalent to B in mod n, then Ka is equivalent to Kb in mod n. This is pretty important. I'm just going to double check one thing. Yeah, I mean the simple part is, let's just say if Ka is equivalent to Kb in mod n, if you bring it out to the other side and factor it, then Ka minus b is equivalent to 0 in mod n. Now, in this case, we haven't assumed anything about. Wait a minute. Oh wait, sorry. Yeah, silly me. You have A equivalent to B in mod n. If you add these up k times, because they're the same congruence, you have Ka is equivalent to Kb in mod n. Yeah, that is the simple part about it. Yes, but this previous part I was showing will come into effect later. Yes. Here's a nice result. I mean, there are multiple easy ways to show how it works, but does anyone remember difference of powers? Okay, basically, if you have a number like ak minus bk, that is equal to a minus b, and then a to the k minus 1 plus a to the k minus 2b, all the way till a b to the k minus 2 plus b to the k minus 1. Hence, when we take this guy in mod n, we're really taking this guy in mod n. Now, if we have a equivalent to b in mod n, that means a minus b is equivalent to 0 in mod n, which is why this guy is equivalent to 0 in mod n, because a minus b is a factor. Hence, we can actually say ak minus bk is equivalent to 0 in mod n, which is why ak is equivalent to bk in mod n. I'll probably switch markers. I realized the ink on this one's gotten kind of weak. Oh yeah, thanks. If you have a black one, otherwise we have other inks. Yeah, there's a. Okay, thanks. Okay, yes, I will make use of those too. Yes. So everything's chill, right, with the fundamentals of number theory? That's good. And here's an important result. If Ka is equivalent to Kb mod n, can we really say this thing? That's the real question. So when you rearrange this out, that's Ka minus b is equivalent to 0 in mod n. Now here's an important condition. If n and k are co-prime, which means they have GCD nk equals to 1, then k can't divide into n and n can't divide into k, which means the only way this has zero remainder is if n divides into a minus b, which actually leads to a result why a is equivalent to b mod n. This is a pretty powerful result. Yes? Sorry, I should say congruent. I think it's because I've been typing too much in LaTeX. I'll say congruent from now on. Sorry, the symbol in LaTeX is /equiv. Sorry about that. And now here's another important result. We'll discuss later, but basically, if you have a prime modulus, you can eventually have a situation where the congruence of two numbers is congruent to 1. We'll discuss this later, when p doesn't divide into a, that is. Now here are here's the tasty stuff. Two very important theorems. The first one is Fermat's little theorem. It basically says if an integer a is raised to the power of a prime, then it is equivalent to integer a in the modulus of that prime. And now here's a nice proof. I'll just do a very short mention to it, because it's not the most common way of proving it, but basically a to the p is also equal to 1 plus 1, like a of them, to the p. And if you use the multinomial distribution, this is actually the sum of the multinomial combination. So P, and then you have your so-called Ka, Kp, and the conditions are Ka plus all the way Kp equals to P, and Ka, Kp are bounded. And the multinomial actual definition is actually just P factorial on Ka factorial all the way till Kp factorial. Now here's where the interesting part comes. If you consider this in your mod P, you're going to have a bunch of terms, which is actually P, a bunch of zeros, P, and a bunch of zeros. And you're going to have a bunch of terms that are basically P, add Ka all the way till Ka1 all the way till, I'll redefine this, sorry, yes, Ka1 all the way till Kap. These guys are not P. And now, just from the formula, this guy literally is P factorial on a bunch of 0 factorials, P factorial, that equals to 1. And this guy is not 1, and it is also not P, just because you don't have any like P left over, which is why when you take this in mod P, this is actually this is actually A1s, and the rest of it's a bunch of zeros, which is why this is equivalent to A in mod P. That's a very nice way of showing it, but when number theory is taught later, there'll be much nicer proofs too, which are much more intuitive. Yes. Any questions, by the way? That's all right, Jeff. I'll show you another appetizing way. Brendan suggested this, and I'll only give a hint though. Consider using the binomial distribution. A to the P is equal to A minus 1 plus 1 to the P. Now just think about how you can use the binomial distribution on this. Sorry, not distribution, expansion. Thank you, Brendan. Yes, yeah, binomial expansion on this. I've been doing a bit of probability, so yeah. And then the next one, this is also pretty important. Wilson's theorem. If you have a prime P, P minus 1 factorial is congruent to negative 1 in mod P. There's actually a really nice proof of this that we'll be discussing. So I guess obviously suppose P is prime and consider this set S. And now here's the important thing. So remember when we discussed AB is equivalent to 1 in mod P? We'll actually be using this idea. This is the idea of congruent inverses, because B would be a congruent inverse to A. And now here's an important thing. Let's just consider the expression P minus K squared. So, oh wait, actually I'll start it from the start, why we need this, because there needs to be a justification for everything that we're doing. So first note that P minus 1 factorial, as you know, is literally 1 times 2 all the way till P minus 2 times P minus 1. And I've purposely ignored 0 factorial. And now consider P minus K squared. This guy equals to P squared minus 2KP plus K squared. If you take this guy in mod P, then this is just equivalent to K squared in mod P. That means P minus 1 squared is equivalent to 1 squared in mod P, which is, not equivalent, congruent to 1 squared in mod P, which is congruent to 1. And if you take in K equals to P minus 1, you have 1 squared as congruent to P minus 1 squared in mod P. And so basically from this, what we can note is P minus 1 squared is congruent to 1 in mod P, and 1 squared is congruent to 1 in mod P. Now, if you guys remember this guy, this is what defines modular inverses. We can say that P minus 1 and 1 are their own modular inverse, which is why when you consider this factorial, which contains all the elements in set S, we can say for sure that P minus 1 and 1, if they multiply with another factor in mod P, none of them are going to have a congruence to 1 because there is no other modular inverse. So when we actually take this guy in mod p, you're actually going to have 1 and p minus 1 intact. Now, you guys might be wondering, what happens to this guy or this guy, 2, p minus 2, all those numbers? Well, from what we found out, only 1 and p minus 1 have its own modular inverse, which means these guys, there'll be another number in here that when they multiply with each other, they will result in congruence to 1. And the reason we can say that for sure is when you take in mod p, this set you see there, S 1, 2, 3, p minus 1, those are the possible remainders, excluding the 0 or the p part. So, which is why when we take this, these will all multiply to 1. So you'll have 2, and you'll have 2's modular inverse somewhere. So 2 times that modular inverse will be equivalent to 1 in mod p, for example. So when you take this back, you'll just have a bunch of 1 products from roughly p minus 2 times, which is why this will just be equivalent to p minus 1 in mod p. And I hope everyone remembers that we can represent this as a negative 2 in mod p, as congruent to negative 1 in mod p. This is a very appetizing proof, I must say. Does anyone have any specific questions on the proof? I guess if not that, we shall move on to the next few parts. There's going to be even more useful revision stuff coming. So the next important stuff is the totient function. The totient of, say, a number n counts the number of positive integers k that are less than n, which is co-prime to n. Co-prime meaning that the GCD of k and n equals to 1. And this is a nice definition. Yes, this is very important. These are the key properties of the totient function. The first one is the multiplicative rule, where if the GCD between a and b is 1, the totient of ab is the totient of a times the totient of b. Now, the way I think about this is, if a and b have the greatest common denominator of 1, then they do not share any primes or any primes raised to the power between them. So when you consider the product, a and b contribute distinct primes to the product, which is why you can intuitively take the totient of a and b as the totient of a times the totient of b. I hope that makes sense. Otherwise, I could show it heuristically. Okay. The next one is the value of prime powers. If p is prime and k is greater than or equal to 1, then the totient of pk is, well, this guy. I mean, this is simply an application of the totient function we have had earlier. You have the p1, k1 minus 1, and you have p1 minus 1. And we have simply done that, but with just p and k. And then we have Euler's totient theorem. This is a really nice theorem because you guys don't have to just bother about the power being prime. A to the totient of n is equivalent to 1 as well in mod n. Now, if I remember correctly, the proof is something that would be discussed in the future because it is tedious, yeah. And here's just a nice application. If you do prime decomposition of 72, then find the totient of 72. You can compute a 23 to the 24 as congruent to 1 in mod 72. So, I mean, 72 does equal to 2 cubed times 3 squared. Yes, 2 cubed times 3 squared. Now, if you consider the totient of 72, just remember our formula earlier. 2 to the 3 minus 1, 2 minus 1, times 3 to the 2 minus 1, 3 minus 1, which is 2 squared times 1 times 3 times 2, which is 2 cubed. No, wait, not 2 cubed. It's 1, 3, 2. This should be 24. Yes. Did I? Sorry, pardon? There is a 2 squared at the front, yes? Yeah, yes, sorry, yes, you're right. I just got lost in my train of thought for a second. Thank you. So that's 8 times 3, which is 24. Thank you, Jeff. Which is why the tangent of 72 is 24. And we know that A, like in this case, we choose 23. The GCD of 23 and the GCD of, well, 72 is 1, because 23 is, well, nicely a prime and does not divide into 72, which is why 23 to the tangent of 72 can be congruent to 1 in mod 72. That's how we actually get the result. 23 to the 24 is congruent to 1 mod 72. And now the next part will be discussed by Jeff. I'm excited about it. Oh, thanks, guys. Oh. I didn't drop the mic. I dropped the actual eraser. But I turned the mic off, so hopefully, yeah. Yes. Yeah.
It's a good mod, right?
I mean, this is good.
Oh, wait, is that the good one?
But you have these two.
Okay. Wait, should I put the mic on? I'll just hold it. Okay, so I'm going to talk about these two like main like sort of theorems. Is it on?
It's been off, so
Oh, shit.
because I don't see a green light. Just switch
Oh,
to
it's on.
flip. Yeah.
Okay, no, it's fine. Yeah, so these are two like very, very important like theorems. You're gonna see them all the time. Chinese remainder theorem and like Bayes' identity. But before we get into that, like I think the Euclidean algorithm is pretty important because it kind of gives us some of these like for free. So what the Euclidean algorithm basically achieves is finding the GCD of any two like integers, right? So let's just say we want to find the GCD of like a and b, and let's just assume that b is greater than a. What the Euclidean algorithm tells us is that the GCD of a and b is equal to the GCD of that should be a, sorry, a and the remainder when b is divided by a. And then we just keep on repeating the process, like kind of like recursion if you do comp, until the final remainder, which is going to be 0 eventually. And then the final non-zero remainder is the GCD. So let's like kind of take a look at what that looks like in practice. So our two favorite numbers, 1, 2, 6, 7, and 6, 7. What is the GCD of this? Does anyone have a guess right now? No. Yeah. I mean, yeah, that's how you do it. Yeah. It's not 70. Okay, that's very helpful. I'm gonna show you guys how to do the Euclidean algo like the long way first before I show you the sort of like shortcut version I just showed you. Yeah, it is one, but let's like walk through it, right? 1, 2, what? No. Yeah, okay, the GC is one, but like let's like prove it, okay? So 1, 2, 6, 7. I can write it as 18 times 67 plus 61. Okay, so that's the remainder when I divide by like 67. So I'll bring that over here and bring that over here. So 67 is equal to what times 61 plus the remainder? Well, 67 minus 61 is like 6, so that's the remainder, and then this will be 1 times that. And then we do it again. So 61 is equal to what times 6 plus its remainder? It would be 10 times 6 plus the remainder, which is 1. And then 6 is just equal to 6 times 1 plus 0. We hit the 0 remainder here. So the last non-zero remainder, which is 1, is our GCD. And this is like the sort of like long way of doing it. If you do it the short way, i.e. you don't have to calculate what, 18 times 67, you just get this, which is basically the same thing. We're looking at like, the GCD of like this and like that and so on, basically. Any questions there? No? Okay, this will be pretty important later, specifically about this, Bezout's identity. So basically, if we're given this integral equation for x and y with these coefficients a, b, and c, which are also integers, then what Bezout's identity tells us is that there always exist solutions x and y to this in the integers if and only if the GCD of our coefficients a and b divide c. And well, in terms of actually solving these equations, well, you'd kind of just like use the Euclidean algorithm. So in this case, I'll kind of walk you through it. So we start at this line, and then we get that 1 is equal to 61. Remember, 1 is the GCD, minus 6 times 10. And then in the next step, we kind of like plug in this. So 6 is equal to 67 minus 61. Plug that in there, and then so on, right? Like if you have like n iterations, you just do it n times. And then eventually you'll get like, this times something plus like this times something is equal to 1, if you can see how it kind of like works recursively. And then that's pretty much like why you need the GCD to like divide, because like this is how you get like the GCD, and if it wasn't the GCD, then there's no way to construct like integers for it to be equal to the GCD or a multiple of them. Yeah? Oh yeah. Okay, so the question now to you guys is, remember previously we were talking about like cancellation and like multiplicative inverses in like modular arithmetic. Like does this tell us anything like about when we can like cancel off stuff? I remember this is like kind of standard notation. This is Z mod B. So like integers modular B. I don't think it was used before, but it's there now. Any ideas? Okay. So let's just say I want the multiplicative inverse of like A, like mod B, for example. And then we have the multiplicative inverse, which is X. And this is congruent to 1. Well, that's the same as saying that AX plus BY is equal to 1. And then you can see why you require the GCD of like A and B, which is like what you want to invert, and the modulo to be 1. Because otherwise you won't have a solution for X, and then you can't find the inverse. It doesn't exist. Any questions? All right. Chinese remainder theorem. So this is like useful for if you have like multiple congruence equations and you want to solve for like a value that like suits all of them. So let's just say we have these like pairwise coprime positive integers m1 to mk. What I mean by that is the GCD of any pair of them is going to be 1. So there's no common like sort of factors besides 1 between all of them. And then I have these like system of equations in congruences. So x is congruent to a1 mod m1 and so on. What Chinese remainder theorem tells us is that there's a unique solution modulo the product of all the like sort of modulars there. So m1 all the way to mk. So let's walk through a little example of how this is like applied. Let's just say there's like x students, and then we split them into groups of 5. Then there's 2 left over, and when we split them into groups of 9, there's 4 over. So we're gonna ask, how many students are there if there's less than 100? Does anyone have like an idea? Like, just make like a guess. Like, yes. How'd you know? Okay, that's one solution, but there's 2 solutions actually. No. No. Unfortunately not, but 6, 7 is one of the answers. Lucky guess. Yeah, here's how you do it. So I'm just going to encode like the question in math, basically. So let's just say that X is the number of students, and then what the previous like question was telling us is basically this information. So X is congruent to 2 mod 5, and X is congruent to 4 mod 9 because they're the leftovers after you split them into like groups. And then what we do next is a bit like weird, so just stay with me. Let's just say M1 is 9 and M2 is 5. We want to find the multiplicative inverse of 9 modulo 5, which turns out to be 4, and the multiplicative inverse of 5 mod 9, which is 2. And obviously that works because they're co-prime. And then what we do from that is we construct the solution this way. So we get that X is equal to A1 M1 Y1 plus A2 M2 Y2. And when you calculate it using all the numbers you just found, you get equal to 22 mod 45. And that's basically what Chinese remainder theorem tells us, is that this solution here, X is equal to mod 22 mod 45, is like unique. Is it like confusing why we like randomly just choose like Y1, Y2 and stuff? Yes, okay. So just think about like this number like in general. Like ignore the mod 45 for now. So let me just write it out. So A1, M1, what was it? Y1, just A2, M2, Y2. Now consider this one like mod M. Well, this has an M here, so it's going to go. And then this one doesn't. But what we just found was this is, what was it? 5. And then this is equal to 2. But remember, mod 9, 5 inverse is 2. So this just becomes, when you multiply it, congruent to 1 mod 9. And then this A2 is just still there. So basically, we're kind of forcing like the solution to like work in this case, because we have this, and then we want to make this like 1, so it like remains, but we want to get rid of everything else. It's a bit like not intuitive if you see it for the first time, but basically you're just forcing the solution to like work in this case. And you know that it works because you have the co-prime like 5 and 9. Yeah, that's it for my part. I'll just give it to Peter now.
Michael, talking to. Alright, tough. Oh yeah, thank you. Awesome. Alright, while Via's doing that, we're gonna talk about chord residues. They're like a thing that exists. So you're gonna be pretty familiar with modular arithmetic so far, hopefully. If not, tough luck. But definition-wise, quadratic residues. Oh my goodness. Nah, oh good. Okay. That's this is why you guys should pull up. Wow, great. It's just let A and M be integers with M is not 0. We say that A is a quadratic residue modulo M if there is some integer n so that n squared is A mod n. A lot of yap, you can kind of think of it as like, what are the possible remainders when you square, like what are the possible remainders modulo M when you square a number, right? So if there's a marker, you can kind of think like, well, if we pick M, oh, okay. Oh, thank you. If we have like M is 3, and if we check mod 3, let's just check square numbers now. So 1 squared is 1 mod 3. So 1 is a quadratic residue modulo 3. 2 squared is also 1 mod 3. And then 3 squared is 0 mod 3. So basically from here, and afterwards it just starts repeating, right? From here you can see that 1 is a possible remainder and 0 is a possible remainder, not 2. So we'll just say the quadratic residue modulo 3 would be 0 and 1. Goodness. So that's all well and good. Why is that useful? IDK. But I guess one reason would be is under certain moduli only a small number of possible remainders are perfect squares. And here's like a little diagram I yanked off Wolfram Alpha. It's like kind of like a table of sorts. If you look at the columns, the columns are kind of like n modulo n, right? And for each row, it's shaded if that number is a possible quadratic residue. So notice that all of these horizontal lines, they are kind of the square numbers, because any square number, intuitively, it's squared. Like for example, 4 is 2 squared. So anything that's a square number is automatically a quadratic residue modulo anything. So that's why you have all of these horizontal lines representing 1, 4, 9, yada, yada, yada. But the more important thing is that notice how it kind of forms like a triangle, right? That's because of like this symmetry. So if you have x squared, that is equivalent to n minus x mod n. I'll let you ruminate on that while I do it on the board. But essentially, if you have n minus x squared, that expands to n squared minus 2xn plus x squared. And if you take that modulo n, anything that has a divisor of n gets cancelled out. So that's just equivalent to x squared mod n. Cool. So that's just basically saying if you split like the numbers into pairs of 1, n minus 1, 2, n minus 2, and so on, if one of these numbers in a pair is a quadratic residue, the other one must also be the same. So each pair basically contributes at most 1. So you kind of have already a bound on the number of possible distinct quadratic residues, and that is just the floor of n on 2. So let's do eager question. Next slide. We have, hence the quadratic residues can be kind of like a filter for various mod questions. And here's like a pretty easy example. Prove that no integer of the form 4k plus 3 can be written as a sum of 2 squares. So I'll give you guys, let's say, like, I don't know, some time to do that if you wish. I guess 1 to 2 minutes, and then we can do that. So prove no integer of the form 4k plus 3 can be written as a sum of 2 squares. I'll give you a couple of hints. Number 1, it involves quadratic residues. Number 2, modulo 4 might be useful, hopefully, probably, maybe, yes, likely. Yeah. Yes, so everyone has had a little think of that, so we'll just go through it, I guess. So solution. Well, let's say it is possible, right? We'll do a classic contradiction. Suppose that 4k plus 3 is a squared plus n squared for some integers a and b, and we're going to consider the equation modulo 4. 4 is a pretty good number because 4k plus 3, it has a k in it, so we can easily get rid of that if we just take mod 4, right? So that just basically saying a squared plus b squared then is congruent to, yes, congruent to 3 mod 4. Okay, let's see, a squared plus b squared is 3 mod 4. If we remember our quadratic residues, it's just kind of like, it's a quadratic residue if there's some number that satisfies like, p, we'll just use p for another variable, if there's some n that satisfies this for some p, right? So we're going to check mod 4, so the quadratic residue is mod 4. So let's just list them all out first. We just have 1, 2, 3, 4, and then we'll square all of it and check. Right, 1 squared is 1 mod 4, cool. 2 squared is 0 mod 4. 3 squared is 1 mod 4 again. And 4 squared is once again 0 mod 4. And then it starts repeating afterwards. So as you can see, the only possible n that satisfies this property is 0 and 1. So we have the quad res, I just shorthand it, quad res of 4 mod 4, I guess, would just be 0 and 1. Okay, well that's pretty useful because if we have two square numbers, mod 4, it has to add up to 3. But we just proven that since the quadratic residues mod 4 are 0 and 1, you cannot possibly get to 3, right? The best you can do is 2 mod 4. So that's basically saying, well, there aren't any a and b such that this is true. And we're done. Awesome. Just rub this out. So moving on. Yes, okay. So this thing, Legendre symbol, it looks kind of like binomial. It is a pain to type up because you can't do like fractions and binomials. But it's basically kind of like an identifying function for quad residues. It's basically saying if, first things first, the specific difference is that for p, the p has to be an odd prime, whereas before quad residues, we can take it mod any number, kind of. And let a be an integer. The Legendre symbol with a with respect to p, from there on I'll pronounce it a on p, is defined by a on p is equal to 0 if p divides a, 1 if a is a quadratic residue mod p, and minus 1 if it's not. So all it is, it's kind of just like an identifier symbol to check if a is a quad residue mod p, right? And that's about it for the function itself. And the reason why it's interesting is it just shows up in a lot of other theorems to help with it, I guess. So some basic properties, these are not too bad. So if you remember from modular arithmetic, well, you have like a is congruent to b mod p. Then in Legendre symbol, then a on p is also equal to b on p. Notice that we get rid of the congruence here because this is actually like a function now. We're not taking it mod anything. So just saying if, yeah. And the next one is multiplicativity. Cool. So if you have some number a times b on p, then that is equal to a on p times b on p. These proofs aren't too hard from just if you just spam modulo and like what quadratic residue means, because if we recall, the whole thing about Legendre symbol is that it's just like a function that identifies whether a is a quadratic residue mod p, right? It's not really anything special. But what's on the next slide? Yes. Probably the coolest part is, well, so far, remember from our a squared plus b squared is 4k plus 3 question, to check if something is like a valid quadratic residue mod something, the best method we got so far is by checking every number, right? It's like, remember doing mod 4, we had to check 0 squared, 1 squared, 2 squared, 3 squared, and then to see if that's like what that all results in. That quickly gets real annoying for like pretty big p, right? Like it's like 40, and then you're kind of cooked. So for bigger primes specifically, we can introduce the law of quadratic reciprocity. So what is that? IDK, yeah, it's here. So the law is kind of like big. I think it's kind of split into 3 parts. I'll explain. So first things first, let p and q be distinct odd prime numbers. The statement of the main theorem is that p on q and times q on p, remember Legendre symbol, is equal to minus 1 to the power of p minus 1 times q minus 1 on 4. And remember from our multiplicativity and congruence thing, this already takes care of a lot of stuff, right? Because for any non-prime integers, like if we want to do like 35 on like 41, we can split 35 into prime numbers. And the only thing we can't do is if it's an even prime number, because remember p and q has to be odd primes. So for even prime number, and specifically minus 1, because for any negative number, you can change it into minus 1 times a positive number. We have these two supplements. They're not generally included as the main statement, I guess, but I've included it because it's going to be pretty helpful. It kind of takes care of every integer, right? So you have minus 1 on p is equal to minus 1 to the power of p minus 1 on 2, and 2 on p is equal to minus 1 to the power of p squared minus 1 over 8. So if you think about it, that kind of takes care of every integer. If it's positive and not prime, we split it into primes. If it's negative, we factor out the minus 1, and then we do the same thing we do with positive numbers. Cool. The proof of these, look it up. But like there's a bunch of proof, but like I think probably the easiest one is something called Euler's criterion, which gives you something that expresses stuff. I forgot. It's in the appendix if you're interested. Why is it useful? Let's do a question. Does the congruence x squared plus 6x plus 15 is congruent to 0 mod 41 have a solution? So if you guys want to give it a try, sure, but I'm probably just going to go through it. Yeah. Okay, I guess you can have a think. Otherwise, Do you wanna try? No? No? Do I have to pick names? Wow, no one wants to contribute. I'm gonna start crying. Yeah, cool. Let's just go through it then. Yeah. So first things first, we're doing quadratics. So remember, complete the square from like year 6, 7, 6, 8. I don't know. That's a good one actually. Yeah, that's great. There is no way, bro. I don't believe you. First things first, we're gonna complete the square. We can rewrite this as x plus 3 squared is congruent to 35 mod 41. Why do we do that? Is because we've been doing quadratic stuff. Get with the program. Yeah, so that's basically saying we have x plus 3 squared such that it's equivalent to 35 mod 41. And then that's saying, right, 35 is a quadratic residue mod 41. And if you remember from like a couple of slides ago, 6 or 7 slides ago, that's basically saying 35 on 41 is equal to 1. Because if we remember definition of Legendre symbol, it's equal to 1 when this is a valid quadratic residue mod this. This is an odd prime. 41 is an odd prime. Crazy, I know. So that's basically saying a solution exists if and only if 35 is a quadratic residue mod 41, i.e. this is 1. Why if and only if? If you kind of think about it, if it's not, then you can't find x plus 3. And the other way around is, yeah, it's kind of just by definition, I think. Yeah. But the hard part is like, how do we find what this is? We can just do what we have so far. Remember, first things first, we have our multiplicativity. We can split 35 into 3 and 5. So this is equal to, I'll write the whole thing. 5 on 41 times 7 on 41. And from there, if you remember, 5 on 41 and 7 on 41 both odd primes. So you have 5 on 41, 41 on 5 is equal to minus 1, 5 minus 1, 41 minus 1 on 4. That is equal to minus 1 to the power of 4 times 40 on 4, which is equal to 1. And same thing here, 7 on 41 and 41 on 7 is minus 1, 7 minus 1, 41 minus 1 on 4, which is equal to minus 1 to the power of 6 times 40 on 4, which is also equal to 1. Wow, what a coincidence. I definitely did not set those numbers, so they did that. Oh, awesome. Ravine. So that just equal to this, as shown on the board. Oh, he's gone. I can see the answer now. So now, we can do our modular, right? Recall that if A is congruent to B mod P, then so does the sign, like the Legendre symbol. So 41 is congruent to 1 mod 4. 41 is congruent to 1 mod 5. So 41 on 5 is equal to 1 on 5. And 41 on 7 is equal to minus 1 on 7. And finally, 1 on 5 is just 1, right? Because if you think about it, 1 is a quadratic residue of everything, because 1 is a square number. And minus 1, if we go back, because I genuinely forgot what it was, minus 1 on P is equal to minus 1 to the power of P minus 1 on 2. So minus 1 on 7 would be minus 1 to the power of 7 minus 1 on 2, which is minus 1. Times minus 1 is minus 1. So what does that mean? That means 35 is not a quadratic residue mod 41, and that means you can't find x plus 3 such that x plus 3 squared is 35 mod 41. Therefore, you can't find like an integer x. So therefore, this thing has no solution. Awesome. I think that's the last of it. Yeah. What's the question, Veer?
The Legendre symbol again, like the 541.
The 5 on 41 to 41 on 5. That's using quadratic reciprocity, right? Because if we remember, P on Q and Q on P is minus 1 to the power of that. So if we flip it, it's equivalent to just timesing it by the... Yes.
Okay. Yes.
Oh, thank you. All right. Nice.
This is an exam eraser from like 2008 or something.
Exam eraser.
Math 101. That's like.
Oh. Free answers. All right.
Okay, thanks. That was cool though.
Okay, so that was sort of a look at all of the theory and background. Now let's have a look at how we can sort of apply these in real life. So I guess a big application of number theory is in cryptography. Yeah, but I guess before we dive into sort of, a lot of numbers, a lot of equations and algorithms, I think it's nice to, I guess, contextualize cryptography as like sort of what are the goals, what are the aims of cryptography, and what is cryptography itself. So I guess story time. We sort of have two characters, at least for now, in our story. We have Alice and Bob, right? And Alice and Bob want to share a message, right? They want to talk to each other. Then this might be over the internet. For our cases today, we'll just assume this message is an integer. Yeah, don't worry too much about the sort of technicalities. Pretend the message is an integer for today. But I guess unbeknownst to them, or known to them, we also have our third character. We have our character Eve, the friendly ghost, right? But Eve is actually not so friendly, because Eve is actually an eavesdropper, right? So they're listening in on this conversation between Alice and Bob. Cool. So I guess sort of aims of cryptography revolve around these three questions, in the sense that from the perspective of Alice, because I might be aware that there might be a chance of someone listening into my conversation with Bob, I might be asking the questions of, can Eve read my messages, right? Sometimes I want my messages to be hidden, to be secret. Can someone listening in potentially read my messages? I might also wonder, can like someone in the middle change my messages, or change the messages that I'm about to receive, right? Because that might also be a problem. And another question might be, am I even talking to Bob at all, or am I talking to someone who might be impersonating Bob? So for the sake of today, I guess for the scope of today, we'll mainly be addressing this first question, which is how can we keep the message between Alice and Bob hidden, so that even if someone else was listening in on the whole conversation, like, is there a way to hide my message? Cool. And now, introducing Teddy.
All right. Do I need to wear this?
If you demount it, like the mouse trap,
Oh, I'll just hold it.
if you want to, but basically, if you see the clip guy, like here.
Oh, I can't be bothered.
Oh, okay.
It's fine. It's fine.
Yeah,
Is it on there? It's not on
when
there.
the green light's on, then it's on. Yeah. I know the clip seems kind of annoying, but just
Pretty,
think of
pretty different.
Tom and Jerry. Call it there.
Okay. Look, I don't know why the slide is here. I was meant to be removed. Anyways. All right, we're going to talk about RSA, which is one of the encryption algorithms. So RSA stands for, yeah, just the authors that like invented it. And it leverages the factorization problem. So this problem states that factorizing just like numbers in general is difficult. What this means is that we don't have an efficient algorithm to factor like a really big number. So given like a really, really big number, computers right now, if we don't consider quantum computers, just normal computers, they can't factor this number in like a reasonable amount of time. They might take like thousands or millions of years to factor. So if we have a number that is the product of just two really big primes, then it's going to be really, really hard, just given the product of those two primes, to recover the factors, which is just those two primes. All right, let's go over how RSA works. So first off is key generation. First, we generate two primes, P and Q, usually 1024 bits each, so really, really big numbers. And then we compute n equals P times Q. So n is really, really big, 2048 bits. And we're going to let our public exponent E be either 3 or 65537. Usually in practice, oh, 65537. I did not say 67, bro. Who laughed? Usually in practice, it's going to be 65537 because we'll see there's like issues if you choose E to be like 3 if it's like too small. But in our case, it doesn't matter for now. All right, more maths. So we compute D, which is going to be the modular inverse of E mod totient N. And we'll see why. We'll see why later. Recall that totient N, in this case, since P and Q are just prime, totient N is going to be just P minus 1 times Q minus 1. Okay, and our public key is going to be N and E, and our private key is going to be D. What this means is that our public key can be known by anyone. So in our scenario with Alice and Bob, Alice and Bob can just like send their public key. It doesn't matter if other people have it. Eve can have it and it's fine. But private key is never sent. It's always kept secret. It's never sent. Oh yeah, and notice here, you must factor N to recover the private key D. So if I never give you the private key D, and you only know the public key N and E, the only way you can compute D is to first factor N, and then compute the totient of N, which is P minus 1, Q minus 1, and then modular inverse to get D. So that's the only way you can actually recover D. You have to know the factorization of N. Why does it say that, bro? Okay, so encryption. Let M be the message you want to encrypt and C be ciphertext. So these are all just numbers. We're going to have C equals M to the N, M to the E, and then mod N. So very simple. And then decryption. Again, really simple. M equals C to the D, and then mod N. All right, why did you add this, bro? What is the, okay, God. Next time I'll actually like review the slides. So why does this work? Recall that this is Euler's totient function. If we have any number A that is coprime to N, and we raise it to totient N, it's going to be equal to 1 mod N. In this case, since we have N equals P times Q, we're basically guaranteed every time that A is just going to be coprime to N. Like in practice, you're not going to randomly choose your message to be one of the primes. So yeah. Since we have computed D is the modular inverse of E mod totient N, by definition, we have E times D equals 1 mod totient N. Therefore, E times D is 1 plus some multiple of totient N. So proof. What is this actually saying? Okay. So we've encrypted by saying C equals M to the power of E mod N. And we decrypt by raising C to the power of D. And we're going to see why this works. So if you raise C to the power of D, it expands to your message M to the power of E to the power of D, which is just power law, M to the power of E times D. And then since we have our identity from before, we have M to the power of 1 plus some multiple of totient N, which we further expand out to get M times some multiple of totient N. And by Euler's totient function, since we have M to some multiple of totient N, we have that M to that multiple of totient N is just 1. So you can kind of just remove that and you're left with M mod N. So that's how the decryption works. Is that all good? Any questions? All right, cool. We're going to move on to a second one, which is Diffie-Hellman. So this is a method of key exchange. Okay, so Diffie-Hellman relies on the discrete logarithm problem. So this is another one of those problems that are like computationally hard to solve. And the problem states that G to the power of x be h mod p. So we know all the numbers here. We know G, we know h, we know p, but we're not given x, which is the exponent. And the problem asks us to find x. So same as the RSA factorization problem, this is very hard to solve computationally. There's no efficient algorithm right now. And we're going to abuse this fact to basically do cryptography. So same scenario again. We have Alice and Bob. And the goal is that Alice and Bob want to arrive at some shared secret. The shared secret is just like a number. And they want to arrive at the same number. But with Eve listening, we don't want Eve to also have that secret number. You can imagine the secret number being some sort of password or key used to encrypt their communications afterwards. All right, so the algorithm is as follows. First, Alice and Bob are going to communicate and decide on a prime P and a base G. These don't have to be secret. They can just send them across whatever network. Eve can know them, it's fine. But they just have to decide on a prime P and some number G. So Alice picks her number, XA, and Bob picks his number, XB. So these are their secret numbers. So they're never going to be sent across this communication channel. They're going to keep it to themselves. Now Alice computes HA equals G to the power of her secret number XA, and Bob does the same thing. So HB equals G to the power of his secret number XB. And then they're going to exchange these numbers. So Alice sends Bob HA, and Bob sends Alice HB. So now if you notice in the communication channel, we've sent across P, we've sent across G, HA, and HB. So everyone knows these numbers. Alice, Bob, and Eve all know these numbers. Finally, to compute the shared secret S, what we're going to do is we're going to, for Alice, she's going to raise Bob's number HB to the power of her secret number XA, which will result in G to the power of XA times XB. Bob is going to do a similar thing. He's going to raise Alice's number HA to by his secret number XB, and he's also going to arrive at the same number G to the power of XA times XB. So it's kind of just like the power law, just some like maths. They both like will arrive at the same number. But crucially, what happens is that Eve only knows P, G, HA, and HB. So P doesn't know either of Alice's or Bob's secret number. Eve doesn't know XA or XB. So Eve cannot compute this, their shared secret S, without first solving the discrete log problem. So Eve will have to find some number. If Eve wants to find Alice's secret number XA, then Eve will have to find like some number XA such that G to the XA is equal to HA. But this is like very computationally difficult when you use really big numbers. So Eve cannot do this. And this is how Diffie-Hellman works, basically. Yeah. All right. Now Will's going to go over some attacks.
Okay. Just hold it, that's fine. So yeah, but in most cases, right, Eve's not just gonna give up. Say they're like eavesdropping, right? They're not gonna see, oh, Alice and Bob are communicating using RSA. I'm just gonna give up now, right? And I guess as often is the case, if Alice and Bob are using some faulty version of RSA, or if they're using RSA exactly as Teddy described, they can actually get attacked, and like essentially Eve can break the encryption. So yeah, now we'll look at some ways that Eve can actually bypass this RSA protection. Cool. So the first attack we're going to look at, I guess, doesn't really have a name. I'll just call it small m. So this happens when the message is really small, right? Say we're communicating only a small number, like 10,000, 20,000 or whatever, such that our encrypted message, m to the power of e, is less than n itself. Well, in this case, our ciphertext is equal to m to the power of e mod n. But since m to the e is less than n, like that's literally just equal to the value of m to the power of e, right? There's no modulo effect here. So because of that, we can actually get the message really quickly. We just take the eth root of the ciphertext. Now you might be thinking, like, why can't we use, like, why is RSA safe in general, right? Why does the modulo change that much? How is this different from just discrete log? The answer to that is normally our messages will be quite big. So when we calculate m to the power of e modulo n, like our resulting ciphertext can equal m to the power of e, m to the power of e plus n, m to the power of e plus 2n. Like there's many different possibilities, right? Because of the modulo. The thing is, k can become very, very big, right? When our m to the power of e, it will usually be like 2 to the power, at least 2 to the power of 100 times more than than our value of n. So because of that, like you would have to brute force 2 to the power of 100 different values of k. Like if you just try to take the eth root, which will take sort of a long time, and as Teddy said, like maybe millions of years. So because of that, normal RSA is safe, but if you have a really short or a really small message, and you just sort of encrypt it as you do normally, that's how you can get attacked, and encryption basically means nothing. One way we can protect against this is by using something called padding. So essentially what this does, or I guess one of the reasons why we use padding. So what padding does is, like as part of the protocol, we'll say we want to always guarantee that our message length is more than, say, I don't know, 2 to the power of 30 or something, right? How can we ensure that? We'll say if our message number is less, we'll just like say append a's to the end of our message, and that will make sure that it's sort of long enough or our number is big enough, right? And then when you receive the message and you decrypt it, if you see a spam of a's behind our message, you know, like, oh, that's just padding. I can sort of ignore it and read the rest of the message, sort of as it is. Cool. So yeah, we can use padding to help protect against having just a small message. Cool. Next, we'll look at Hastard's attack. So for this, we'll look at a specific type of encryption called broadcast encryption. It's commonly still uses sort of RSA, but it uses RSA for a specific purpose. In this case, say we want to send a message to 3 different recipients, right? And they're sort of out there in the world. We might not have a direct connection to them, so we might want to broadcast this message out towards them. So yeah, we have our 3 recipients. They have public keys N1, N2, N3. Essentially what we'll do is we'll just encrypt all of our messages sort of as normal with RSA. So each of the ciphertexts are message to the power of E modulo their respective public key. And then at the end, we'll just send these messages out into the world. And the idea behind this is only the people, like, you can only decrypt the corresponding message to your own public key, right? Only person 1 can decrypt C1. They won't be able to decrypt C2 and C3, etc. And if you don't know sort of the private key, you won't be able to decrypt any of the messages. So yeah, that's broadcast encryption. But if you just do it sort of, again, as it is, there are some problems that can arise. So Teddy mentioned earlier, if we use our value of E as being 3, that can lead to some problems. This is one example where this can lead to a big problem. So first step is assume that E is 3, or like if E is 3, then you can use this attack. So I guess the first step in this attack is to compute some value of x such that x is equal to m cubed modulo n1 times n2 times n3. I guess we'll look into why this is true or why you can even find an x in the first place, but this might be something nice to think about. Why do we know that there exists an x that satisfies these conditions? Once we do that, we just take the cube root, and that is supposedly going to recover the message. So that's the attack. Let's have a look at why this is true. So yeah, recall our ciphertexts are all equal to the same message to the power of 3, right? Because that's how RSA encryption works. So because of this, we can form this system of equations. C1 ciphertext 1 equals message cubed modulo n1, etc., etc. So this hopefully looks similar to something that we saw earlier today, which is Chinese remainder theorem. But before we can directly apply Chinese remainder theorem, we have to first make sure that n1, n2, n3 are coprime, right? The GCDs are not equal to 1. Yeah, so I guess we'll address the case where n1 and n2 share a common factor first, just so we can use Chinese remainder theorem next. So if n1 and n2 share a factor, well, without loss of generality, so if any or two of them share a factor, we can use Euclidean algorithm to really quickly find what that common factor is, right? And recall that each of these n's are literally formed, only have two prime factors, right? They're all just p times q, for primes p and q. So as soon as we find one factor, division is also a pretty quick algorithm. So if we find the common factor between n1 and n2, we can factorize n1 really quickly, and bam, sort of we've broken RSA, right? Because once you know p and q, you can figure out the decryption key quite quickly as well. So yeah, like if any of n1, n2, n3 share a factor, we've already won at that point. So we don't even need to use this attack. So because of that, like, do that as a check first. If it doesn't work, we can proceed with this attack, which is also guaranteed to work. So yeah, the next step is we can, because of Chinese remainder theorem, we know that we can always find some value of x, which is congruent to m cubed mod n1 times n2 times n3. Yeah, and I think Jeff provided a method for how we can go about finding this x as well, which is pretty quick. Once we have this, remember that, I guess in general, our message m will always be less than n1, n2, n3. This is just to ensure that we can recover a result when we're decrypting, right? We want to, like, once we decrypt, we always just want to get our result straight away. So m is less than n1, n2, n3 individually, which means that m cubed is less than n1 times n2 times n3. Hopefully at this point, this is looking pretty similar to, I guess, our small message attack, because the x that we've just found is equal to m cubed mod n1, n2, n3. So because of that, we just use the small message attack from before. Because m cubed is less than the modulo that we're taking it, n1 times n2 times n3, we could just take the cube root of x, and that will get us back to our message directly. So yeah, this is a pretty cool attack. And in fact, we can generalize it as well, right? So like we can see that any time our encrypted message m to the power of e is approximately the same size as n1 times n2 times how many people you're broadcasting the message to, we can sort of do a similar attack using like Chinese remainder theorem first, and then using sort of this small message attack, right? And in fact, when n is e is equal to k, assuming our message is less than n1, n2, n1, n2, n3, like all individually, we also know that this attack will always go through. So yeah, this is, I guess, a problem with like just using sort of textbook variants of encryption algorithms, because you'll run into these problems. Again, we can use padding to help us, like not only by beefing up our message, but also because if we use a different padding for every different recipient, like say, to recipient 1, your padding will be, I'll just append 1s at the end of your message a lot. And for recipient 2, I'll append 2 at the end of your message. And for recipient 3, I'll append 3 at the end of your message. Then each message is different, which means that you don't have sort of this trick, because like you're not sending the same message to the power of 3, you're sending 3 different messages, because they're slightly different because of padding. Cool. Okay. The third attack we're going to look at is called the, I don't know how, Franklin-Ryder attack. The conditions for this attack is, I guess we have sort of another Alice-Bob scenario. Alice's public key N and E. Bob wants to encrypt 2 messages, M1, M2, to send to Alice. So we can use this attack when we know that the messages that Bob is sending are very, very similar, right? So say we know M1 and M2 are related in some way, and we could describe this relation using a polynomial. This is when we can sort of execute this attack and actually recover both messages. Cool. Yep. So the way we're going to go about this attack is we're going to define 2 different polynomials. So G1 is just x to the power of e minus C1. Right, E is the encryption key used, C1 is the first ciphertext. And for our second polynomial, for our second function G2, it's going to be f of x to the power of e minus C2. So yeah, recall f of x, I guess, is just what we're going to call the relationship between m1 and m2. So say Bob was sending, I don't know, 2 consecutive numbers over to Alice, and he encrypts both of them and sends them over, then we know the relationship between the numbers is just f of x equals x plus 1. Cool. So we define these two functions. Nice, we'll have them on the side. So the first observation we can make for these functions is if we plug m1 into both of them, it will both result in 0, right? Because if we plug m1 into g1, we get m1 to the power of e minus c1. c1 is just equal to m1 to the power of e, so they cancel each other and we get 0. Similarly, if we plug m1 into the second equation, f of m1 is equal to m2, and then m2 to the power of e is equal to c2 as well, so they both cancel. So what this means is that m1 is a root of both of these equations, right? And these equations are both polynomials. They are both x to the power combinations of x to some integer power. So because of that, these polynomials share a root of x minus m1. Because we know this, we can compute something called the polynomial GCD. So you can do, we can use the Euclidean algorithm to compute like the GCD between two numbers. Well, for integrals, you can do something very, very similar as well. In fact, the operations might be basically identical. But yeah, you can actually compute the GCD of these polynomials. And what that will be all of the factors that are common to both polynomials. Right? So we'll recover like a smaller set of factors. And within those factors, in general, it'll only be like x minus m1, sort of as the only factor that's common to both polynomials. Because of that, if we recover this factor of x minus m1, we've basically won, right? Because we've found what m1 is equal to. As for m2, since we know the relationship between m1 and m2, like it's pretty easy to get from m1 to m2 as well. So we just need to sort of plug that into the function again. Cool. So yeah, that's all the attacks I'm gonna go through today because that's all we have time for. But here are some other attacks you can look at in your own time, left as an exercise to the reader. Firstly is something called Wiener's attack, or the small d attack. The guy who came up with this was called Wiener, or his last name was Wiener, and it operates on the fact that like when your decryption key is small, you can again break RSA. So that's why it's a small d attack. Cool. There's Smith's attack, which is a really common attack as well on RSA, quite popular. There's meet in the middle algorithm. So this is just an algorithm that slightly speeds up, I think is it factorization, discrete log factorization.
Just like brute force.
Brute force. Yeah, it's a more efficient brute force algorithm that can crack RSA slightly quicker than normal, which might be useful for again when some of your parameters are a bit small. And finally, if you have a quantum computer, it's GG's already. Like all of these problems are rely on the fact that you don't have a quantum computer, and they're solved quite quickly by Shor's algorithm. But luckily, quantum computers are really bad right now. So we still have a while before we need to look at those quantum options for cryptography. Cool. That's all.
Okay, thank you to our presenters. So thank you again to Will, Teddy, Peter, Veer, and Jeff. So can we get a round of applause for them again? Wonderful. Okay, so we're done with the slides now, which comes to the fun part of trying the worksheet problems and the, what would you call them? CTFs, yes. The link is up there. You can grab your worksheets from up front. We have pizza coming in about 10 minutes, so just wait around for that. So eat up some of the problems first before you get full on pizza. Yes, and we're going to get a photo now with the two banners. I'm going to end the recording, and thank you all for coming. If you have any questions, please ask the presenters or ask me. We appreciate you all being here. This is probably the last CPM workshop for the term. Besides there is a DP, no, not DP, Graph Theory CPMsoc workshop next Wednesday from 5 to 7. And Spa this Saturday. So go to that as well. Yeah. Yes. It's next Wednesday, 5 to 7. Oh, where? Electrical Engineering GO2 by everyone. It should be. Hey,